So thanks for joining us today. My name is Pavel, and probably you know about me and my company, Septimal Mind. We are a small Irish consultancy working on big things. Our work includes Izumi Reflect, which is a portable reflection tool for Scala, DIStage dependency injection, biotype classes hierarchy, and CATS interop Zio module. And today we will talk about build systems for modern projects and how we can make them better. We are working on a new build system for Scala that might change how things are usually done. I have to warn you that in this talk, we are just exploring some ideas and details of our work, which is still in progress. It's not something you can start using straight away. Also, our time is limited and the domain is vast, so this talk will be dense. I'm not able to ask you any questions because unfortunately this is a second attempt on recording this talk. But I have to say that our build system is based on multiple ideas. We on multiple ideas from projects like NixOS, Nix Package Manager, Gentoo Linux Portage, our own project DIStage, and Bazel. So there are many Scala build tools which are available on the market, but many in the engineering community are not happy with them. People complain about slow build times, problems making builds reproducible, complicated build definitions, complicated debugging, unclear error messages, limited flexibility, and limited extensibility. So, what's wrong with the current build systems? The problem is that they use a lot of ad hoc solutions and they have some design flaws. SBT and MIL are good for Scala, though SBT has many issues with DSL ergonomics, features, and build speed. MIL is way better, but people still complain about its ergonomics. Gradle is somewhat declarative, but does not support Scala well. Maven has issues in almost every aspect. Bazel and Pants are really good from the design standpoint, but they have limited Scala support, and there are many complaints about their ergonomics. Something is definitely wrong if you need tools built on top of Bazel, which just try to improve its UX. Let's talk about some important ideas for understanding the topic. A build system is a tool that creates values called build artifacts by running different tasks in a specific order. To explain, think about cooking. So imagine that you want to make a breakfast omelette and you have a recipe with eggs, milk, a mixer, a pan, and a stove. The recipe tells you what to do step by step. In the programming world, we call recipes functions, each giving you a result. You may make an order and say what dishes you want. The kitchen prepares your order according to the recipes and fills a tray with your dishes. When your waiter comes to your table with a tray and names the dishes before handing them over to you. So the tray acts like a heap of the values, what the functions give you. These instances are identifiable by some values, like, for example, strings, for which we have an established identity. And our step-by-step build scripts can be represented as a directed graph. This applies to any computer program. If there are no loops, conditionals, or jumps in the program, we can represent it as a directed acyclic graph. In Turing incomplete languages without control flow instructions, programs can be represented with specific form of directed acyclic graphs called project networks. Project networks just state what actions we want to do and their order. Turning a sequential Turing incomplete program into a project network graph is a simple automatic task. Project networks, they have many important properties. First of all, any project network is guaranteed to finish in a finite time. And also, they are easy to schedule. They can be executed very efficiently because steps without connections can be done independently. Project networks represent optimally scheduled programs. In the world of build systems, there is an important but not always clearly stated idea. When creating programs, we often have to consider different platforms, compiler versions, and many other configurable aspects. This leads us to add extra settings into our build definitions to cover with various build modes. So our building process becomes multimodal, supporting different modalities. To explain, think of a chef making a meal customized for different diets and calorie plans. The steps change for each type of breakfast. In Scala, we have various compiler versions, different platforms like JVM, native image, Scala.js, and Scala native, and potentially many custom settings. And it's clear that we need to explicitly support different build modalities. And just as a waiter combines multiple breakfast orders into one request to the kitchen, with build tools like SBT, we might ask to build our projects in different modalities. However, SBT doesn't natively support this. Using plus with an SBT target means running the build independently multiple times, once for each compiler version. And importantly, SBT doesn't have built-in support for different target platforms. So we need a specialized third-party plugin for that. And it doesn't support any custom modalities. So two more important concepts are heterogeneity and hermeticity. A heterogeneous build involves using multiple different technologies. For example, it might use various code generators like gRPC, or it might build native extensions, or just use multiple languages like both Java and Scala, or perhaps Kotlin. Hermeticity is a simple idea, but challenging to implement. It means that the build always produces the same results for the same sources. In other words, a hermetic build is completely isolated from the build environment. A fully hermetic build is essentially a pure function of sort, but achieving this goal is very difficult. In our builds, we use a lot of third-party code, and much of it was not designed with hermeticity in mind. This means it has many sources of non-deterministic behavior. Before we proceed further, let's define what we actually want. I would say that we want to build multimodal heterogeneous projects with millions of lines of code quickly, reproducibly, and with ease. So, our ideal build tool should provide top-tier Scala support and smoothly handle multimodal projects, covering all Scala-specific approaches. It should also excellently handle heterogeneous projects like native libraries and code generators. We want build definitions that are clear and simple, written in a way that's easy to understand. And in pursuit of efficiency, speed, observability, and hermeticity, which is the utmost level of reproducibility, we require builds that are not only quick, but also fail fast and are easily debuggable. Distributed build support is also crucial for modern workflows. And also, we need strong testing capabilities that include proper and sound resource management and effective resource sharing, or memoization. We also want a unified test reporting API that can be easily integrated with new test frameworks, even our own custom project-specific mini frameworks. Current build tools serve many purposes well. So why consider a new build system? The reason is that existing build systems designed for Scala aren't well suited for large industrial scale code bases, except for Bazel, which has its own drawbacks. When dealing with large industrial code bases with hundreds of thousands or even millions of lines of code, we face slow builds, complicated build definitions, that are hard to write, read, and debug. And also we face development environment integration issues like even medium-sized SBT projects can take a long time to be just imported into IntelliJ. When the majority of industrial projects are multimodal, with a mode representing an option for our builds and offering multiple possible values, like platforms, compiler versions, and application feature flags are typical examples of these modes. Existing build systems may have limited or suboptimal support for multimodal builds. Like while SBT supports compiler versions, it can't process different versions in parallel, and it leaves support for other modes, the third-party plugins. And for projects needing heterogeneous builds, like making native extensions or generating code, the situation is not great as well. And again, one of the biggest pain points is the quality of development environment integration. So the question is whether we really need a new build system. Well, not necessarily. We could improve an existing one, considering Bazel or at the very least Gradle as potential options. However, it seems there is a reluctance to invest in such improvements, and personally, I think that if making existing solutions better requires a lot of effort, it might be more practical to create a new system tailored to our specific needs. This aligns with our approach to dependency injection, like after spending years improving the developer experience of Spring and then Juice, we eventually created DIStage, a solution that outperforms any our dependency injection method by a significant margin across various measures. So, Septimal Mind is currently developing a build system that aims to fulfill all these criteria. Allow me to present the Grandmaster. Please note that the Grandmaster is still a research project and isn't ready for immediate use. For the rest of the talk, let's explore the ideas and design principles behind the Grandmaster. From a design perspective, Grandmaster incorporates concepts from DIStage dependency injection, Nix package manager, and Portage. These systems are based on the ideas of generative programming and staged execution, principles that form the foundation of Grandmaster. In Grandmaster, we enforce declarative approach to build definitions. A key component known as the planner translates these declarations into a directed acyclic graph comprising individual actions. This graph undergoes a validation stage before being interpreted. Given its nature as a graph, the build plan is designed to be traversed in parallel. Taking inspiration from DIStage and Portage, both of which embrace multimodality, like DIStage supports configuration access and Portage supports use flags, Grandmaster inherently supports multimodality and all the intricacies of Scala. Similar to the hermetic approach of Nix package manager, Grandmaster tries to be hermetic by storing action outputs using input hashes as cache keys. All inputs and outputs are hashable and serializable, enhancing support for incremental and distributed builds. In contrast to Nix, Grandmaster goes beyond supporting pure actions and introduces cacheable and non-cacheable actions. Cacheable actions, though impure, can be cached, for example, like snapshot downloads, while non-cacheable actions require re-evaluation each time. Notably, if a non-cacheable action produces the same result, subsequent actions benefit from input hash-based memoization, avoiding unnecessary re-evaluation. And this slide provides a high-level visualization of the Grandmaster workflow. The process begins with a declarative build definition and a set of build routes collectively forming the build input. This input is then fed into the planner, which generates a directed acyclic graph of actions. Following this, the graph undergoes validation before being interpreted to produce the final build artifact. It's worth noting that although this slide has been presented as past event, the YAML displayed here is no longer in use. We have since evolved our approach but this slide retains the original depiction for continuity purposes. You may be wondering about the current status of the project and when we can expect an opportunity to build something with Grandmaster. The project is currently in the early stages of prototyping, making it challenging to pinpoint a release date. We currently have a functional prototype of the execution layer and artifact storage, along with a library of actions sufficient for building simple projects. However, our focus is on developing the front-end build definition language and the key component, the planner. It's still a work in progress. While the source code is not available to the general public at the moment, it will be once we have a working MVP. However, there is a possibility that we may not complete the project due to resource constraints as a small company. It's you need you need a lot of time and labor to create a nice build system. So before we continue, I would like to inquire about what you believe to be the most challenging aspect of this project. Is it the execution layer, the front-end DSL, the planner, or the library of actions designed to meet the diverse needs of users? And surprisingly, the aspect posing the greatest challenge for us is the front-end DSL. We did not anticipate the difficulty in finding a solution that is both flexible and straightforward to both comprehend and write. Designing a build tool involves balancing contradicting goals. For instance, increasing flexibility reduces convenience and vice versa. The trade-off also applies to build performance, where the aim for speed conflicts with both extensibility and convenience. Every component requires careful balancing of these trade-offs with particular emphasis on the front-end language, as it is significantly influences and shapes the overall system design. So originally for the prototype, we chose to adopt a fully declarative domain-specific language using YAML and later TOML to encode the abstract syntax tree, bypassing the need for a custom parser. Despite YAML's inherent issues, it wasn't a major concern. We crafted an AST for our front-end language in Scala and just implemented a YAML reader to produce instances of that AST. Like essentially YAML served as a means to avoid developing a custom parser. And in retrospect, it might not come as a revelation, but we encountered significant challenges in creating a declarative domain-specific language that is both flexible and extensible. And after investing considerable effort in coding, we decided to scrap the first attempt upon realizing that the complexity has had become too overwhelming. And we experimented with a simpler generic DSL, allowing actions to be referred to by names with generic parameter sets. However, we abandoned this approach as it closely resembled Ant and proved to be flexible but inconvenient. Eventually, we realized that to enhance convenience, we required macro definitions or templates, and after incorporating template support, we recognized the need for template expansion within templates, making YAML and TOML form hard to read. Like it became just difficult to differentiate between action definitions and template calls, and difficult to read and write build definitions. And we also explored the idea of Scala DSL. However, realizing that any implementation would resemble SBT code on the slide, and considering many issues such as slow startup speed associated with using Scala as a scripting language, we abandoned this approach as well. And if you worked with the Nix language, you would know that it's something like JSON, but with added functions. So the Nix package manager is a robust heterogeneous build system built on the Nix language, known for efficiently and reproducibly handling large code bases. However, it has drawbacks, particularly in multimodality support. Despite this, the Nix language is a proven solution for describing complex builds. In our experimentation with a generic YAML DSL, we realized that our approach resembled what the Nix language does. Consequently, we chose to develop a Nix-like language, a JSON, but with functions. It's a work in progress, and so far the progress looks promising. The code on the slide provides a glimpse of the idea. We are uncertain if it will be the final form, as there are other potential sources of inspiration. One such source is the Nix sibling, a package manager and build system named StalX, which you can find linked on the slide. Please take a look. Please also note that the front-end language formulas are evaluated in totally pure manner into a JSON-like data structure. When this structure can be analyzed by automatic tools like an integration plugin for your editor, and when it will be fed to the planner. Essentially, the Grandmaster language is a fancy templated engine intended to make your build definitions cleaner and more concise. As mentioned earlier, Grandmaster is not available for download or use currently. The source code isn't accessible to everyone yet. We plan to release it once we have a functional MVP. However, there is a possibility that the project might not be completed due to our limited resources as a small company. As I said before, creating a build system requires a significant amount of time and effort. If you could offer funding, we would greatly appreciate it. And additionally, if you're interested in contributing to the development, it would be fantastic. So we still have several open questions that we haven't addressed yet. And one of the challenging issues is the integration with the development environment. Specifically, the project model of IntelliJ IDEA is notably rigid and outdated. It lacks support for multimodality, conditional source inclusion, and conditional artifact builds. And while manual exclusions are available, they don't provide the needed flexibility. Currently, we are considering the option of generating multiple IDEA projects for different modalities. However, this approach makes it difficult to effectively share sources between modalities. The more appropriate solution would be to develop a custom IDEA plugin, but this entails a substantial amount of additional work for our team. Another unresolved question pertains to how we should support incremental compilation and whether implementing a compiler server is necessary to keep the compiler active and reduce load times. Many existing build tools rely on Zinc, and it seems a viable choice for our project as well. However, we haven't conducted a thorough evaluation to confirm its compatibility with our model. Additionally, we are keen on avoiding scenarios where memory leaks from the compiler or a macro impede builds, a concern observed with SBT and IntelliJ. And if we opt for a compiler server, careful evaluation is crucial to address potential issues, although we haven't yet assessed with specific problems. Let's consider another complex aspect. It's evident that planning everything ahead of time is not always possible. For instance, when we download a zip file and need to apply transformations to each file within, we can't predict the number of the number or names of these files in advance. And this implies the need to plan as deeply as possible, execute part of the build plan, and potentially replan. And while this approach seems logical, the concept of dynamic replanning is extremely difficult to work with. Originally, we believed it might be essential for DIStage, but subsequent exploration revealed that alternative terms to describe the domain and nesting and nested planning are better substitutes for dynamic replanning. We would like to avoid the necessity for dynamic replanning in a practical industrial build tool. However, if the need arises, we envision integrating it into the Grandmaster model by introducing a specialized yield action. This action would trigger replanning when reached by the interpreter, providing a flexible solution if required in the future. So, thanks for your attention. If you have any questions, please feel free to ask on our Discord or Telegram channel. Also, be sure to visit our GitHub page, give us some stars, and follow us on Twitter.